Welcome to my solution of the binary search tree practice quiz. So let me restart the timer. So I need to implement the find method on a binary search tree. And the binary node has a left and right, so let's start by Java docking a binary search tree method. Public class binary search tree of type E, generic. It has the root of the tree, binary node E root, comparator decides order. Just spell it right. Comparator decides the order. Comparator E comp. So that we're going to use comp to decide if a node is an item in the node. A node item is less than or greater than or equal to the data in the node. So finds the given item, returns the reference to the item in the tree. At param item, the item to search for, at return a reference to the item in the tree, or null if item is not in the tree. So we're going to return null if the item is not in the tree. So public E find E item. Now in a binary search tree, the item is all items in the tree are less than the root, or in the left hand side, and they're greater than the root in the right hand side. So we're going to need to recursively traverse the tree. So we're going to do a return find E item, and we're going to start at the root. So now we need to create our recursive method, private E find, that takes an E item and a binary node E node. And so we're going to say, first off, if node is null, that means we could not find the item in the tree. We've traversed to the end, we got to it, we said we had to go left and there was nothing there, or we had to go right and there's nothing there. So if we got there, then the item is not in the tree, so we return null. Okay, so now we can say, we know that the node's not null, so we check, we say int comp val equals comp dot compare. We're going to say node dot data and item. So if the node, I'm going to swap them. Item node dot data. So we look at the current node's data and we compare item to that. So now, if comp val is less than 0, which means that item is less than the node's data, we need to search, we return find item node dot left. So we need to search left because the item is less than the data in the node. So we need to search the left subtree. And we'll recursively search the left tree. Else, if comp val is greater than 0, that means the item is greater than the value in the node. So we need to search the right subtree. Item node dot right. So if it's less than, we got to go left. If it's greater than, we got to go right. Else, we found them to be, we found they're equal. So we want to return node.data, which is the reference to the item in the tree. And is that complete? We start at the root. If the root is empty, we return null because there's nothing in the tree. Else we compare the data, the item we're looking for, to the node, the data at the node. And then if it's less than, we got to go left. If it's greater than, we go right. If they're equal, we return the value in the tree. And that is done. Let's Javadoc that. Recursively search for item at param item, the item to find at param node, the current node in the tree, at return a reference to the item in the tree, or null if it isn't in the tree. Okay, so what is the big O of this operation? Well, we know that if the tree is full in items, that the depth of the tree is basically log n. So we only have to go down the depth of the tree. So we're always sort of dividing the problem in half. You're not considering half of it, so you're always dividing the problem by half. So the big O is log n. So we're always dividing the problem in half, and that means it's a log n operation because we decide left or right. Thank you very much.